I'm Brandon Besack.
I'm Idan Hershcovich.
I'm Charles Hill.
This is Brendan McFadden. This is Sean McFadden.
I'm Nicholas Wegfahrt. Modern games offer no satisfying ability to adapt gameplay in response to a player's individual experience with the game. In particular, games do not have any adequate means of assessing or responding to a player's stress. Stress is very important for determining a player's experience. Too little stress implies a lack of engagement, and too much stress implies the player is overwhelmed. There are only a few solutions that offer anything close to what we are proposing here, Effectiva being the closest. However, it cannot efficiently solve our problem. Effectiva only accommodates for detection using solely a web camera. It does not incorporate further sensors to enhance assessment. Effectiva is also specifically targeted towards academic and research projects, limiting its audience. This academic orientation has not led to a conservative approach to resource usage, creating issues with its use in more resource-starved environments. Nevermind is a great example of the potential of our system. This game grew from an interactive media thesis project to become a successful horror game. The way the biofeedback system tailored the experience was touted by many users. There is so much more that could be done and attempted in games and software in general if only a system like this were more widely available and tuned to the task.
The Ash API intends to fill that void. By using video data and allowing for optional devices to leverage biometric data, developers are able to tailor their experiences per user with a much lower bar to entry. Our system facilitates a direct feedback with the developer system in order to better maintain a player's attentiveness and stress. Currently, developers' best guide for estimating player stress is the flow graph on the left, using skill and difficulty as factors to tune gameplay to the general player stress state. The valence and arousal space gives a more precise understanding of the individual player's stress for games to respond to.
The Ash API is currently built for Windows 10 computers. Our system supports most types of conventional webcams. And for better assessment, plug in a Nulog galvanic skin response sensor. Both devices support plug and play, allowing for you to swap devices when needed. Once you have the GSR electrodes on your fingers, you're ready to play. To achieve precise analysis of facial expressions, the system requires adequate lighting as well as proper framing of the user's face.
Ash API is our way of allowing users to access our systems in a safe and reliable manner. Written in C# and designed for Unity, the current version of Ash API supports a wide variety of functionalities to access the main core of our application. These core systems consist of our main application, camera and GSR devices, and machine learning architecture. One of the more standard features of Ash API is our readout system. Ash API allows for robust data readouts that consist of a wide range of data from single instance session data to a trend of information across a time frame. In the example code to the right, we see examples of how to access standard readouts and trend data. For example, the function getLastReadout will return an Ash data object consisting of the most recently calculated data. These data can then be translated and casted into different formats via our built-in functions such as toFloat and toArray. Additionally, Ash API supports threshold for affect levels with support for event propagation for crossing upper and lower boundaries. These thresholds can be configured by the user to allow for a wide variety of event-driven circumstances. In the event to the right, we can see how to add a lambda event when an upper threshold is crossed. Each threshold object contains its own event handler, allowing for custom boundaries for upper and lower thresholds within the same system. Ash API also features a wide variety of tools and methods for device manipulation. Here, users can reconfigure selected devices as well as get detailed information about compatible devices. Below, we can see an example of modifying the currently selected camera and GSR device. The methods setActiveCamera and setActiveGSR can be used to modify the main application's currently selected device. Additional functions, such as getConnectedDevice, can be used to help determine proper device information in order via a device information object. Ash API also comes with a wide variety of data collection-based event systems, allowing for callbacks to update the programmer on operating state changes. Currently, Ash API supports events for camera and GSR devices disconnecting mid-session, face framing errors, face lighting being too bright or too dark, as well as detection when the face is occluded. The example to the right shows adding events when a camera disconnects and notifies the system. Welcome to the dashboard. This is our application of linking the common user to the Ash API. This can be used for developers as a sort of testing method or testing tool for the API, or it can be used as the common consumer as a health tracking application. So there's three main components on this profile page, which is the first page you are booted into. You have our quick links, our mood breakdown, and our session feed graph. These quick links are simply just documentation and sort of helping the user understand how to work the dashboard. The mood breakdown is our last three sessions generalized into percentages over the day. So for example, on this middle day, I had low activity for roughly 35% of my time on the application. And then we have this live feed, which is simply our most recent readout of the Ash API if it is connected. This is the current flow of data coming into the application that is coming out of the main Ash API, and it's being displayed here. So another page we have is the history page, which allows users to get more in-depth history on their kind of trends, their stress values. Specifically, we allow the user to go back really as far as possible, but we only show about 1 month at a time. The information is kind of generalized, just in a way that we don't want to kind of overload them with like hundreds of values, so we'll kind of just give you a nice little generalize of you seemed uninterested on this day. So you had a day that you were very, very uninterested, while you weren't very stressed out, so it could have been like a boring day. And then like this day you seemed very stressed, so you had a very aggressive, stressful day. So going back to the profile page, another big feature of the Ash API is the dashboard is a minimized view. So pressing this minimize button will convert the dashboard into an overlay that will always stay on the top of your screen here. It's a semi-transparent little overlay that is locked in a corner of the screen that can be configured. Its design is to just be as like non-intrusive as possible, but also still showing you trends of your data. We want to show you your current value and how that trend is working, so we're showing you like a minimized view of that live feed graph as well as our perceived version of your stress. So yeah, that is the dashboard application known as Ashboard. It is available at ashapi.dev.
Stress is interpretively flexible. It could mean anxiety, physical exertion, cognitive load. A more satisfying definition of stress comes from the study of affect, where affect is the feeling or expression of emotion, measured on two primary metrics. The first, valence, is the positivity or negativity of an emotional response, and arousal is the emotional intensity of a response. Feelings of higher valence and lower arousal correlate to lower stress, while feelings of higher arousal and low valence correlate to high stress.
In order to meet our numerous performance metrics in regards to things like accuracy and system utilization, multiple machine learning architectures had to be created. The team had to plan out architectures that preferred accuracy with heavy overhead, or quick static models with fast training time and even faster evaluation. The first two of these architectures are architectures A and B. Architecture A consists of two independent SVM models combined with an SVR in order to produce results. Architecture A is flexible around our GSR data stream, as the weights can be changed in our sensor fusion matrix. Architecture A, as is B, is incredibly fast to train. Architecture B was created as intent to skip the sensor fusion idea entirely and directly append our GSR data to our face data. Finally, PCA was used to shrink our feature space for both model architectures. These models were combined with traditional feature extraction methods, including utilizing 128 pixel anchors and histogram of oriented gradients. Our third and most robust model created consists of numerous parts combined into a full pipeline. First, raw images are fed into our modification and extension of a VGG16-based CNN classifier. Our GSR data is then fed through a bidirectional RNN post-feature extraction. The RNN takes in our phasic decoupled GSR data and attempts to associate our SCR and MSCR temporally with our incoming frames. These are then fed into our sensor fusion matrix, whose weighted results are fed into a simple LSTM memory model in order to ensure temporal connection between frames.
In order to properly show off the machine learning capabilities of the Ash API, we can take a look at the following demonstration showcasing our CNN/RNN model being applied to our training and testing dataset, AMIGOS, provided to us from the University of London. The first set of videos, to the upper left, represents how our CNN/RNN architecture produces consistent results and maintains stability over a long assessment period. A 1 minute and 30-second video has been sped up, placed next to the results for our model. Note that the red data points represent our predictions and the blue data points represent our ground truth labels. Note how our model has a break in evaluation when the participant looks down, as a face could not be found. Also note how our results hover around the ground truth labels with minimal outliers. Next, we can take a look at the participant below. This participant is much more expressive, which we can see by the sharp increase in both valence and arousal. Also note how our model can pick up on subtle emotional changes not provided by the ground truth labels, as noted by the upward curve towards the next batch of labels. Finally, we can take a look at our feature extraction methods for our configurable SVM approaches. Here, we are extracting 68 facial anchors.
In order to properly ensure our models have the best possible accuracy, as well as being computationally feasible in a client machine, two separate performance metrics were utilized. System performance, in terms of time to complete an assessment, CPU load, and memory usage, and accuracy. Our CNN architecture performed an assessment on 10 frames with a sequence length of 2 and a mean of 2.80 seconds. This longer evaluation comes paired with a much more robust model, and a model that is hardened against things like shadows, sun lighting conditions, and orientation. The model classifies utilizing less than 20% of a single CPU core and less than 500 megabytes of RAM. Our SVM architecture, on the other hand, are much faster and less resource intensive. These models utilize less than 10% of a single CPU core and use less than 250 megabytes of RAM, but this comes at a cost. These models are much more vulnerable to things like orientation and much more sensitive to lighting conditions and other anomalies. There was no discernible differences between timing tests for both SVM approaches. In order to wrangle the inherently sporadic nature of our classification results, we devised two separate accuracy metrics. The first one, known as the circle of confusion, adds binary classification capabilities to our generated results as we check if our generated arousal and valence pair lies within a circle around the ground truth value, where the radius of the circle is a hyperparameter that can be tuned during training. The next metric is a combination of and proportional scoring of numerous other distance metrics, resulting in a more traditional accuracy metric.
The user can plug any generic webcam and, optionally, a NuLog GSR into their computer to begin receiving affective assessment. The Ash core system is responsible for asynchronously reading in data from these devices, processing it, and determining an affective assessment. Each of these tasks is performed by centrally controlled, distinct components of the core system. Ash core controls its usage of system resources by using buffered communications with an efficient C backend for its inter-process communication. This adds a layer of resiliency against resource starvation, appropriate to functionality within games. Additionally, it aims to keep memory usage low by minimizing message size. Flexing around resource availability, as seen in this table, our API achieves a nominal 1.31 megabits per second throughput of sensor and assessment data, flexing up as high as 3.4 megabits per second. Owing to the API's goal of minimizing resource usage and buffer design, we achieve a 17-second latency from the moment a stimulus or error is captured to the time it is available through the API. Despite this latency, our assessments remain continuous, such that we achieve no less than 6.9 samples per minute, even when starved for resources. These samples are then smoothed via a Lagrangian interpolation to stimulate near continuous resolution for the convenience of the user.
Over the course of development of the Ash API, we have used many libraries and softwares, including, but not limited to, the Windows SDK, Keras, TensorFlow, Electron, and React. In order to manage our progress, we've used a number of utilities, including GitLab for source control, Jira for task management, OneDrive for file storage, and, as we've moved most of our operations increasingly online, Discord and Zoom to maintain our regular communications.
Due to the challenging circumstances surrounding the term, we found ourselves having to scale back the implementation of a number of features, but we still want to deliver on our vision. By September, we intend to enhance the abilities of the Ash API by integrating such features as the autonomously adaptive research usage, perform improvements to our assessment to resource consume ratio, and release a Unity package for Windows systems. Additionally, we seek to expand behaviors of the Ash API with some long-term goals. These include an asynchronous actor-critic approach to effective assessment, model individuation, and support for more generic forms of GSR and smartwatches, and the portation of the Ash API to additional OS platforms and the expand to the Unreal Engine.
We've provided some important links if you'd like to learn more about the Ash API. We've provided links for our senior project website, the Ash API website, and our GitLab repo. Thanks for checking on our progress. If you have any questions, we'd love to hear them in the link above. And we hope you'll follow us as we continue to grow the Ash API.